Okay, I guess we are going to start. I guess this shows that homework was really hard or what? Okay. Or we are just getting to the end of the semester and people are tired. All right, so today I'm going to talk about the hybrid between graphical model and deep learning. This is quite a bit an active area of research these days, so I'm going to basically touch the surface, and there are lots of stuff going on. Hopefully, after this, you have enough background to go and read papers. So that's the purpose of this talk. Things are moving very fast in this intersection between deep learning and graphical model. So the outline of today's class, we are going to talk a little bit about the ways that we can combine them. More specifically, I'm going to talk about jointly learning features and graphical model and learning process at the same time. We are talking about a specific class of these models called Variational Autoencoder and also GANs. And then we can tell you how this can be incorporated in general structure. So there are a lot of slides I have to tell you that probably I won't be able to go all the way to the GANs. If I could not, I'm going to start the next class to finish this lecture, and then my postdoc are going to give you a little bit of flavor on application from in a computer vision. Okay, so what is the motivation to combining graphical model and deep learning? So graphical model allows us to encode domain knowledge. For example, you have seen that in the context of parsing and how we construct the model. That was basically the discussion that we had at the beginning of the class, that like basically we use either we learn the structure or we learn some causal model, we talk to an expert in the field, and the graphical model is a very natural way to incorporate this domain knowledge. Neural networks are really good at feeding the data. They have a lot of flexibility, and they have shown very powerful performance in many of the benchmarks. So it would be very nice if we can combine them all together so that we can use the neural network to learn better features and use graphical model to incorporate domain knowledge. So, so today's lecture is about mostly that, like how we can combine these two together. So the key idea of the first part is mostly instead of using hand-engineered features, handcrafted features, it would be great that feature learning is also part of our training process. So it's basically we're using neural network to learn the features for the graphical model. So I'm going to talk about the first part, which is basically using neural network to learn features for hidden Markov model. So hopefully you remember these slides. We have shown to you several times. So this is a Markov model. And so the factor graph, circles represent random variables, square represents factors. And hopefully you guys remember that like this, what these factors are representing so far. So if you remember, if you want to do part of speech tagging, so for example, for a simple sentence, time flies like an arrow, and we want to see what is the probability of assigning these tags, noun, verb, so on and so forth, to each of these verbs in the context of sentence, we can use hidden Markov model to do that. And each of these factors, either binary or unary factors, are basically for this discrete graph is just a table. And at the end, I think we discussed it several times that the joint distribution is going to multiplication of all of these factors with some normalization. So if the factors are not normalized, we have to normalize it with z, but sometimes we decide to use a normalized factor that in this case z is going to be 1 because each of the factors are normalized. So this is basically the case when you have a directed graphical model. So here is I'm showing the start of the sentence, and then like time flies like an arrow, and I have to compute this latent random variable, which is the tagging of each of these nouns in a sentence. And so in this case, z would be equal to 1, and I can get rid of it. And the factor is going to be all normalized factor. So this was hidden Markov model. So one of the ideas that basically, it was basically introduced back in 1992, which is, I don't know, many of you guys probably were not born. So the idea was that, well, how can we combine neural network with HMM? So here is the general structure of the hidden Markov model. And so we usually, in a vanilla version, we use this as a device represent our observation, and these are our discrete states. So let's say that, let's be more specific. Let's say that we want to use this to model for basically transcribing speech to a sentences. So for example, we want to hear the voice and then say that like the guy is pronouncing P, T, G, and so on and so forth. So this is, of course, it is natural to use HMM because, you know, the alphabet or character that we detect at time t is kind of dependent on the time point, previous time point, because you want to make sure that the sentence or the verb, the word that you are extracting as a word that the guy is pronouncing is in an English sentence. So it makes sense to be dependent on a previous one. So one way of doing that to use hidden Markov model. So the states are this discrete state. So it's basically letters without sound in English. So P, T, K, B, and so these are discrete states. And the observation is Y. So the joint distribution of Y's, which is observation, and the states can be written as follows. So we have transition probability and emission probability. And one of the ways to model that is that, like, for example, we can have a moving window over this wave, and then we extract some features, some hand-engineered features from this sound. So you know what I'm saying. So it's like, so let's say that this is the wave of the speech that this guy is talking. So, and then we can have a moving window, pass it through some feature extractor, and then get some features from that. So it can be multi-dimensional features from each of this moving window. And then you want to detect that in this time period, he's pronouncing, for example, D or F and so on. So the idea back then was that, okay, so we should have some sort of emission distribution for that, and we most of the time, out of basically computational convenience, we use very simple parametric form for that. So for example, we can use multivariate Gaussian distribution for our features. First of all, that doesn't mean that it's most of the times for computational convenience. That doesn't mean that the Gaussian distribution, multivariate Gaussian distribution, is a good likelihood for that, for the features that we are using. And it's very hand-engineered features. So why not, instead of using Y as an observation, using neural network to extract features directly from for each of those at the same time. So if this layer represents the observed features, let's not view it as an observed random variable, and let's learn the features jointly. So we are assuming that X is actual observation, that is the signal that I told you, that is the moving window that goes over the signal and extract features. But instead of thinking about extracting features, think about the actual signal. We are not extracting any features. It's a raw signal there, right? And then we are passing it to neural network, and the last layer represents our features. Make sense? So the parameters of this neural network is unknown, and this is your raw signal. And this is the last layer, the multidimensional features that you want to extract from it. You don't know the parameter of this network, and you want to use the same network to extract features from that. Is the setup clear, what we are doing? So there is a little bit of confusion in this notation, and the reason it's confusing because here I'm using circles to both represent random variable and also the hidden layers in this neural network. So let me make it clear. So when I'm using circles, the colorful circles, I'm talking about the nodes in a neural network, which are not necessarily random variables. These are just like a function, intermediate layers. And when I'm using white circles, I'm talking about random variables, right? Okay. So this is the intermediate hidden layers. Last layer extract the features that of course, we have to learn the parameters of this network in between and plug that in our latitude. Yes?
So this is the neural network that's extracting the features position independent, use the same neural network.
Yeah, so let's say, because you have to do some sharing. Otherwise, it's going to be a lot of variables. It's not going to be very fun. But yes, that's a good point. I'm using the same. So I'm viewing that as my feature extractor. So instead of using, I don't know, for example, Fourier transformation or Wavlet transformation, I said that I don't want to commit to any of those features. I just have a function, I just have a mapping between raw signal, which is X, and X features. And I don't want to commit. If Fourier is good, then my network is going to learn it. Is the setup clear? Okay. Now, okay, so this is basically our structure. So remember the structure of our graphical model. We had transition probability that here I'm representing by A, and emission probability that here I'm representing by B, right? So transition probability correspond to this factor, and emission probability correspond to these kind of factors. Okay. So now also remember that to do inference in HMM, we had this forward-backward algorithm, which was basically a message passing. So the ingredient of this forward-backward passing was 3 messages. One message that says that what is the probability of state, let's say that this is a state number t. So what is the probability of y1 to t given the state and the state of, so this, let's say call this st being I, given the parameters of the model. So this was my forward message, and the backward message was basically all of these messages this side. So all of these y's from this point on, all the way to the end, and the joint distribution also with respect to this guy. So this is, I had a forward message and backward message. So this was basically, I'm just re-explaining forward-backward algorithm. And what is the posterior probability of ST given all of the observed YTs? So this was the ingredient of my forward-backward algorithm. Forward message, backward message, and the belief. Right? So this was, I can write the joint distribution as basically going, so alpha I t, right? All the way going to the end, right? So this is the joint distribution because I want to see if I go all the way to the end of it. So I've incorporated the joint distribution of this guy, this guy, this guy, and this guy, and all of them together. That's going to be all my forward message. This is going to be my joint distribution, right? Okay, now to move forward, remember our ingredients for the graphical model for any of the machine learning algorithm. We need to have a training. So in this case, our training would be set of, so this signal that I got from the let's say phone, and somebody transcribed it to different letters, A, B, C, D, P, whatever. So this is going to be my raw signal, the tagging, and also the function that maps the raw signal to the tagging. So what would be my f function in this case? I need a function that goes from raw signal to the tagging, right?
Conditional probability.
Yes, exactly. So it's going to be the conditional. So basically the structure of this model. So I extract features, I plug that into my graphical model, and I compute the conditionals, that basically the result, the byproduct of my inference. That would be my function. And what would be my loss function here in this case? What should I do for loss function? If I have a model, one way to learn the parameter is maximum likelihood, right? So my maximum likelihood is going to be joint distribution of the states that I've observed and the raw signal. So it's going to be my forward model all the way to the end of it. Okay, so that's going to be my loss function. And I just have to plug that in, compute the gradient, and work it out. right? That's all. So the main ingredient data, function that produce my tagging, and the loss function, which is maximum likelihood. So now, if you go back, this is a slide that you have seen before in previous talk, that all of these deep learning algorithms are basically function composition. So in this case, my function composition, this part is my feature extractor, and this part is my graphical model, right? So this is my graphical log likelihood of my graphical model, and this part is my feature extractor, which is neural network. And this is more or less the gist of ideas of combining graphical model and deep learning, and using deep learning to do feature extraction. You can view the entire thing as a gigantic function composition that graphical model represent how this function is going to be combined after some layers up, and function composition going to extract features for you. Is the setup clear? Okay. And as usual, as is always the case for graphical model, sorry, deep learning, the engine, the underlying engine for graphical model is chain rule. So I have to be able to compute this chain rule. So going back to the vanilla version of feed-forward neural network, very simple case of having only one hidden layer. Remember how we did it. So we had an input that is basically passed through a linear function, passed through some nonlinearity, linear function, so on and so forth. And then combine at the end. For example, if you have, let's say, like a two class classification, pass through some sort of like a sigmoid function, makes our loss function. That was the vanilla version of the feed-forward neural networks. So how we are going to combine it? So remember, we had the forward layer that goes from my input x and produce my y, and we have a backward layer that compute the gradient. So the forward layer start from features, linear combination, nonlinearity, linear combination, nonlinearity, and loss function. So the backward layer starts from layer back, and basically bunch of chain rule composed with each other to compute the gradient of each layer. That was the main thing that we always do in deep learning. So how I'm going to adapt it for this case? Remember that in my case, when I'm combining neural network with a hidden Markov model, my first layer are still neural network, right? So I do the same thing that I do in the neural network. My input raw data pass through a linear layer, so which is basically this, and pass through nonlinearity if you wish to use nonlinearity, and then goes all the way up to the last layer. So to the last layer, which is basically extract features from raw data and compute an embedding for features, right? The low dimensional representation for features. So far, it's just neural network. Up to the last layer, we have to compute the loss function. And the loss function is coming from our neural network. And this loss function here, in this case, is the log of the joint probability of our tagging and our features. Now, this is raw data, and these are features. Is this clear? If it is not, interrupt me now. Yep? Okay. So the loss function is coming from our graphical model. The rest of it is just vanilla version of deep learning. I mean, you can use whatever you want, but it's the simplest example that I can provide.
What would the joint probability of the tagging giving the maximum likelihood?
Yes. So I'm assuming that you are given a tagging for also given a wave, right? You are given a tagging for each of these. So let's say that this is the wave that you heard over the phone, and I divided this into, let's say, 3 windows. And I said, here this guy pronounced P, here pronounced T, here pronounced, I don't know, M, right? So this would be my S, this would be my X. My raw signal is X, this S is the tagging over that. Make sense? Okay. So now,
Oh, so this is like a supervised.
Oh yeah, absolutely, it's supervised, yes. Yes, that's a good point. So I'm talking about the supervised case. Haven't talked about unsupervised case. Okay. So now, remember that this is X, this is S, right? This is like the entire set is S. The Y, which is a layer in between, this is the Y. The deep neural network goes here to extract Y from X, and Y to S is our graphical model. That's basically the gist of the idea. Make sense? Feel free to ask questions if it's not clear. Okay. Now, so this is my forward model. There is no, so if I want to learn the parameters of the graphical model, so basically the parameters of the factors here and the weights of this neural network, the rest is just chain rule. So how the chain rule works, remember that this was the forward message all the way to the end. So I have to open up my, my forward message, which is a bunch of the for loops, right? The message goes from the beginning, which is the start, goes and how do you compute the messages? So you get from the whatever message that you got from the previous one, you pass it through factor sum over all of the state and send it. And this is like get the message, multiply, sum. Get the message, multiply, sum, right? So if I have, let's say T state is going to be T for loops. But now it's easy. Nowadays it's actually very easy for you because you can actually write it as a for loop, for example, in PyTorch or Autograph. So these for loops get opened up inside of your computational graph. So it's very easy to, the same way do you actually do the message passing, is your message passing is part of your computational graph. So, so the way I just like want to write it easier is like all of the message all the way to the end, normalized by BT is going to be the gradient. So the gradient of that can be even computed in a very nice way. And then the rest of it is just a chain rule. Pass it through the previous layer, and previous layer. And this computation, like basically nowadays, you don't do any computation. You just let, I don't know, PyTorch or TensorFlow to do this computation for you. Make sense? The backward layer is just chain computation. So your forward message passing is part of computing this log likelihood. Okay.
You have Gaussian distribution in the middle.
What is that?
You have Gaussian distribution in the middle.
Oh, yes, yes. So that's a good point. So remember that the graphical model that I had was this. So this was my S1, Y1, S2, Y2, Y3. I still have a Gaussian between this, right? So this factor here is multivariate Gaussian. But I'm not assuming that it's observed. I'm assuming that it's a result of my, my feature extractor. So basically, I'm assuming that the latent space feature, latent features that are unobserved are Gaussian distributed. But that doesn't mean that my original X is Gaussian distributed. It says that, so it's like this. Massage the data in a way that after embedding is a Gaussian distribution, so that it fits my assumption. Unlike feature engineering paradigms that says, I'm going to extract features, cross my finger, assume that's Gaussian. Why is Gaussian? Because that's the only one that I know how to compute easily. Make sense? Yeah. So for your graphical model, you still need to have this probabilistic assumption. So your transition probability is going to be CPD. This is CPD, is normal CPD, because these are discrete state. And from here to here is still Gaussian. But you are not assuming your input signal is Gaussian. You're assuming that your latent space features are Gaussian, which here your neural network has enough degree of freedom to transform the data and make it Gaussian. And you see resurrection of, this is like 1992, but you see the resurrection of this idea when you're talking about variational autoencoder. Okay, so this is basically the backward message to compute the gradient is just a chain rule. So let's see some experimental result with this. This is we are still talking about Bengio's paper back in 1992 when he come up with this idea of combining neural network with hidden Markov model. So the task is to recognize the phenome. And I'm assuming that speakers are independent and all of the assumption that we need to make this experiment work, but the states are all of these alphabet that does not have sounds, like T, M, G, we want to detect that. This is our state. And the metric is accuracy. Now, so the model that we are going to compare with each other is that, okay, let's combine these three models. First model is only using neural network, ignoring the dependencies between these letters. So when you're hearing the sound, let's assume that I'm training just feed-forward neural network and basically try to detect the label of each window independent. So if this is the wave that you got, so I divide it into three windows and I pass them to the neural network. And so view this as like, this is my X and this is my S, and I don't assume any dependencies between this network. So it's feed forward. This is my first model, it's neural network only. The second one is combining neural network and HMM independently. So you can assume that, well, let's train a neural network to detect S, to predict S, and train them independently, and then plug that into your HMM. And the third one is you train them jointly. And this is the result. So not incorporating a structure, which is basically viewing it as just a simple classifier, ignoring the dependencies between them, it achieves something around 50% classification. Not bad, but still there are a lot of room for improvement. If you do them independently, first train the neural network, fix the weights of the neural network, and then feed that to HMM, resulting into a boost because you're incorporating the structure, but it still is close to 80%, less than 80%, but like 75% or so. And if you jointly train them, because you are satisfying the assumptions of the model, so it's basically the assumption of the model is still Gaussian, and you are training them jointly to make sure that assumption is satisfied because you're modeling the joint likelihood, that improves the significant boost. So there is a value into learning the graphical model and neural network parameters jointly. Make sense? Okay.
So the advantage of neural network plus HMM is you model the link between this state and the previous state, so you can get more information from previous.
Yeah. So the difference between this one and this one is that this one ignores the structures. So think of each of these windows. It views as a single classifier, says that give me the wave in that window, I'll try to detect this T, G, try to detect the tag. It's like a classifier, multi-class classifier. Ignores the structures. This one says that what if I train NN, neural network, fix the parameters, and then plug that into HMM. So my parameters are fixed for neural network, but I'm incorporating the structures post hoc. So this is neural network with HMM. So they're not jointly trained. So HMM trained after NN is trained. And this one is trained jointly. So these two both incorporate the structure, except that this one is like first NN is trained and then HMM, while this one NN and HMM are trained jointly.
When you say structure, it means you can take
the dependencies between both. Exactly. Yeah. And one of the reasons is that like if you train this independently, there is no, so remember that you had this layer between S and Y, and you assume that S to Y is Gaussian. There is no guarantee that the result of, so I'm assuming that like, we are training NN, you cut the last layer, and that's your feature. Nobody says that's Gaussian, right? But if you're training them jointly, it forces them, because if it has a fatter tail or has a different distribution, a skew distribution doesn't fit. It says that change the parameter so that this is satisfied. Make sense? Okay. So, and of course we can do that not just for directed graphical model, also for undirected graphical model. So going back to the example that we started with, so you can remember that basically undirected graphical model was multiplication of bunch of factors and normalized by z. So going back to the same part of speech tagging that we have, so if our factors are not normalized, we have to normalize them by z. So, but again, our factors are just bunch of tables, unnormalized tables. Univariate and multivariate factors is just unnormalized vectors. What if we use the input features to train these factors, to basically fill in the parameters inside of these tables? That's the idea of basically combining CRF with neural network. So it's easier because these are unnormalized, and I can easily train any neural network to fill in the numbers inside of this. And that's basically the idea. So again, going back to the same idea, so let's say that we are given our raw features that are here is x1 through xm. Here I'm not necessarily sticking to my previous example. For example, we could have used CRF to part of the body. So remember the deformable model that we had, that we are given. So let's say that somebody is showing you the videos of the individual in front of the camera, and you want to tag part of the body. So for example, this is torso, this is lower arm, this is upper arm, this is upper arm, this is lower arm. And of course, you need some sort of graphical model because it's very unlikely that my torso is on the top of my arms, right? So in order to incorporate that, you can use conditional random fields. So now one idea would be so the classical way of doing that is I can basically think of it as a bunch of moving patches that extract features from the image. So I can patchify the image and extract some hand-engineered features. Well, if you want to combine it with the graphical model, you can go and extract. So from each of these patches, you can fit it into some CNN and extract features. And the way that you can extract features, so this would be, for example, the input into my patches. So it's going to be the output of that would be filling the numbers in my factors, unary factors and binary factors. Right? So I can train either different neural networks for each factor. I can choose to share some of them together. I can do whatever I want. But that's the general idea. Is the general idea clear? So I can, yes.
So how would you train the neural networks in a supervised fashion for this?
So I'm assuming here again that somebody has given me an input image, and this. So let's stick to the same example that I told you. So I've given an image. I've given a coordinate of the torso, upper arm, and lower arm. Right. So this is what I'm given. Now, so this is my input would be image, and the output in this case, let's say call it S. The S would be the coordinate of the top of this, the line that goes from the top of the torso to the bottom of the torso, top of the upper arm to lower arm. So it's going to be 2 coordinate, 2 coordinates, 2 coordinate, 2 coordinates, 2 coordinate, 2 coordinates, and similarly for right hand. Right? This is my output. And my graphical model has to incorporate this information that, well, if this is the bottom part of my arm, so this is the coordinate of bottom part of my arm, the upper part of my lower arm should be close by. So you cannot have this upper arm and the lower arm here, right? Because they're attached to each other. So my graphical model is going to incorporate this kind of information. And like usually the form of the way that these input structures are usually taken. So So in this case, I do have unary. So let's say that in the example that I gave you, so let's say that I'm given an image, and this is the guy in between. So this is the torso, so this is the head, this is the arm, and this is the torso. So my unary term is going to be head. This is the patch of the head, goes back to the produce the coordinate for me. So it's going to be x, y of the head. Right? So this is input image, and this is going to be my unary term. And similarly for the other one, I'm just like, it's so small that I don't want to write the arm, and so on and so forth. So I can use the neural network to fill in the unary term. I can also use the neural network to incorporate the binary term. So in this case, the binary term is going to be, so if this is the head and the torso, and the upper arm and lower arm, sorry, my drawing is not that good. So my unary term extract features from the image, and my binary terms incorporate the dependencies between the head and lower arm, upper arm and lower arm. So, and I can use graphical model to fill in this information, or I can say that, okay, now those information should come from prior knowledge. I have lots of choices on which part can come from graphical model, which one cannot. Make sense? So, so this is just, I don't go through the detail of that, but like you, hopefully you get the idea that like how CNN and CRF can be combined with each other. So here I'm showing you the detection rate for part of the body tagging, and you see that if you have a model that jointly trained, it produced better detection rate compared to the case that I showed you earlier. So it's basically the same thing. What if we use hand-engineered features, which is this one? What if we first train our neural network, fix that, and then put that into our CRF? And the one on the top is that, what if we train them jointly? It's basically the same idea. So that there's a value into training them jointly. So this was one of the ideas that how we can combine graphical model and neural network with each other. So the gist of all of this idea is, at the beginning, the one that I discussed so far, is that we want to use neural network as a feature extractor. But we don't want to do this step. We don't want to first extract features, train our neural network, fix the values, and then train the graphical model. We want to do it jointly, and we see that there is an improvement in training jointly. The idea that the reason that it results in improvement is that when we are using graphical model, at some point we have to make some parametric assumption about our joint. So for example, about our factors, the form of our factors, form of our unaries, and when we are training them jointly, the model tries to fit to our assumption better. While if you do it separately, there is no guarantee that the hypotheses that you have in your model are met. So there's a value to train them jointly. Yes?
So when you train the neural network and the graphical model separately, what do you put as the output of the neural network?
So in the example, the original example that I told you, you can train a simple classifier. So for example, so let's say that somebody has given me this as a training data. So this is my training data. And so my input is going to be this image, the patch around this, and the output is going to be the coordinates. I can easily train a regression, right? The regression that input is my patch image, and output is coordinate of the one on the top and coordinate one of the top of the R and bottom of the R, right? Independently, I can train them independently. Make sense or not? Still.
Do you track the coordinates directly from the image, or why do you need to train them?
So you want to say that, so you think in this case you are training a detector, right? Mm-hmm. Okay. So the detector here is that, so let's say you are given an image, entire image. Your detector should say that This is the coordinate of upper arm, the upper part of the upper arm, and this is the coordinate of the lower part of the lower arm, right? This is your output. You can view this as, okay, one way to do that is input is image, entire image. Output is two coordinate, x, y of this point and x, y of this point, right? And you can train a classifier that only detects the upper part and lower part of the upper arm. You can do it for lower arm, you can do it for head, you can do it for torso. So you can train to say that if I have upper arm right, upper arm left, lower arm left, lower arm right, right? I can train four neural network for each of these. Fix the parameters and feed that to my CRF.
You have to manually label the.
I'm assuming that it's already provided. Yes. Yeah. So this is all in the context of. So I'm going to talk about unsupervised in the following slide, but here we are talking about the supervised case. Yes.
And then when you want to use the trained neural network to extract features, you would feed this. You would use the same image on all of those, not just patches, right? The whole image.
Yeah, so it depends how. So one way to do that is to either provide the whole image, and you have a lot of choices. So sometimes you want to say that you want to give it an image and say that how far it is from the boundary of the patch. That's one way of training it. Another way of training it is to provide the entire image and say that which areas are producing. So you can design it many different ways. It doesn't even have to be a regression. You can say that I can pixelate the image into like a bigger pixel than just like, let's say, merge a bunch of pixels together. And I can classify pixels as upper part or lower part. So this way, you don't give a coordinate, you get a rough, like a heat map of the coordinate. So you have a lot of choices. But what I want to tell you is that if I do it this way, I do it separately. So I train a classifier, cut the last layer, that's my feature. That's one way of doing it. Okay. So this was all in the context of supervised learning. I'm given an input data, image or audio or anything else, and there's a structures into whatever I want to predict. For example, if I want to do part of speech tagging, there are a lot of dependencies. If I want to do part of body segmentation, there's a lot of structures into relationship between them. And everything is, so it's fully supervised way, but in whatever I want to predict, there's a structure into it. And we saw that there's a value into learning, training my feature extractor, which is my deep learning, and the graphical model. What if we want to use this in an unsupervised fashion? Oops. So in the following, I'm going to talk about two classes of algorithm that are can be used when not everything is provided and you can use it in an unsupervised way. The first class that first was introduced around like 2014 by Kingma and Max Belling is Variational Autoencoder. And since then has been a lot of variation and has been a lot of interest into that model. So what is the general idea of the Variational Autoencoders? Hopefully you guys remember this slide that when we were talking about evidence lower bound. And if you remember, we had different point of views, different ways to explain what this evidence lower bounds look like. So if you remember, when we were talking about evidence lower bound, we said that like sometimes if you cannot do inference exactly, you can either cast it as an optimization problem or as a sampling. So this was an optimization problem. And we want to compute the KL divergence between the posterior that we are interested in and some parameterized family, and we want them to be close. And evidence lower bound was to avoid this contradiction that, like, well, if I can compute the KL between the posterior that I'm interested in and the parameterized family, if I know that, I don't need to find something closer to that. So evidence lower bound was to find the lower bounds to marginal likelihood. Hopefully you guys remember this graph that we had back then, that this was PD and this was the KL, and this was evidence lower bound. So we said that this is elbow. Hopefully you guys remember that. So we had different views toward how the elbow can be explained. One of the views toward explaining elbow was that you can view this maximizing lower bound as an optimization problem that has y as an input, and we have some approximation family, which was here represented by Q, that is parameterized somehow. We usually go for parameterization that's easy. We know how to compute the parameters for that. And then I can decompose elbow into two terms. The first term was the reconstruction terms, which means that if I draw a sample from my current belief of the posterior and plug that into likelihood, I'm going to reconstruct the data very well. And the second term was sort of like a penalty term. So this penalty term says that the approximate posterior should not be too far from the prior. So this was one of the views of the elbow. And also another view that we had was this encoder-decoder point of view. So we can represent the same term slightly differently by saying that these two terms can be viewed as encoder-decoder. The first term, so basically, the first term is accepts the data and represent into lower dimensional representation Z, or basically in other words, going to abstract the data into a code. And then the model that I'm interested in is going to reconstruct the data back. So you can think of this as data in goes through encoder, which my encoder was my approximate posterior, going to produce some code, and then I'm going to pass that through my model, which is my x given z. I'm going to reconstruct x back. So this was decoder. So this is another way of viewing approximate posterior and the likelihood together. So the likelihood was trying to decode from Z, and approximate posterior trying to abstract the data. And our goal is to find the approximate posterior, which is as close as possible to the actual posterior. The reason that we couldn't compute this was that, like, to compute this, if you write it as a Bayes rule, you can write it as joint distribution, px, and we said that this is hard to compute. And this is why we need to resort to this approximation. This is another way of saying the same thing. So this is basically our slides from when we were talking about variational inference. You guys remember this? Any ambiguity about this? Nope? Okay. Now, the general idea of variational encoder back then was that, okay, so you told us this is how elbow is, how I'm going to parameterize Q. So the Q, if you remember, this Q was coming from some sort of this is the family of all Qs. So the Q is belonging to this family. This is kind of like a, nice family, no fight. And and this is the actual distribution of the posterior, and you want to find a member of this family which is very close to the actual posterior. So this is the KL distance between P, ZX, and QZ. So I'm going to call this guy Q star. Right? This is a family. This is parameterized by phi, and I'm going to find the closest one. This was the general idea. Now, the question is how I'm going to parameterize Q phi. If you remember back then, we talked about mean field algorithm. So one of the idea of the mean field was that what if I'm going to assume the fully factorizable form? So if I have Z1 through Zm, I'm going to assume fully factorizable form. So and that's my parameterized family. So the two main ingredients of variational autoencoder is that, so let's reduce the parameters and let's force all of these factors to share the parameters with each other. This is called amortization. Because if you remember, in a very vanilla version of the mean field, we have a bunch of factors that all multiply with each other, right? And each of them have its own parameters. What if I force all of them to share parameters with each other? This is called amortization. So one example of that is, what if I use my input data and pass it through some embedding, which, or I would say encoder, to estimate some parameters of let's say Gaussian distribution. And then my Q phi is going to be just normal distribution. It may sound so simple, but in fact, this is a very powerful way of representing this. The reason it's powerful is that given x, QZ is normal distributed. But the parameters are function of x. So another way of viewing this is that both mu and log of the sigma, which is the parameters of the Gaussian, are all function of x. So if I want to write the QZ, right, the QZ is not going to be normally distributed. Makes sense why it's not normally distributed? If I integrate out for all x's, for each x, given x is normal. But for different x's, it's going to have a different mean and different variance. So if I integrate that out, it's going to be basically any crazy distribution, as long as it's smooth. Okay, so it's as if for each x, which x, I'm going to approximate it with a little normal distribution. For each x is going to be different. So that was the main ingredient of the variational autoencoder. So I'm going to dive into that in more detail. So if you think about it as a big picture, so you can think of it as this. So the data is given to you. So, and there is some coding space, some abstract coding space. That the coding space is this Z space. And your actual model, the model that you are interested in, goes back, get the X, reconstruct D. And so this is your decoder. And your encoders get the data and map it back to your code space. And this is the idea of the encoder decoder. You have some space of codes, which is Z space. Your encoder gets your input data, map it back to the code space. Your decoder gets the code and reconstruct the data back. And similar to idea of the encoder decoder, you want to make sure that there are minimum loss of information in this encoding decoding process. Right? So this is the general idea of any encoder decoder. If your encoder and decoders are powerful and good match with each other, they can abstract the data as much as possible with minimum amount of code, and your decoder can reconstruct the data as well without any missingness or loss of information. But another way of viewing the same thing is that you can view it as a mapping of the distribution. Remember that your QZ was, so remember that this was normally distributed, right? Normally distributed with something which is function of this, function of x. And so you can think of it as condition on x, QZ condition on x was very simple distribution. It was just a Gaussian distribution, 2 parameters. So you can think of the variational autoencoder as a way that warps one distribution and creates some crazy other distribution. So you can think of this as some code space warped through the encoder and produce something very approximately complicated. So another way of saying the same thing is mapping between distributions. Simple distribution passes through decoder to get very complicated distribution that represents your data. Is this general picture clear? Okay. Now, remember the elbow. So at the end of the day, all we have was this elbow, evidence lower bound. That was KL. So remember the elbow was expectation of the log of the joint distribution QZ, and Z is coming from my Q. So, and my Z can be, I'm just making that condition on X. Okay, so this, what I wrote is just, I rewrote the same thing in one line. So this is my evidence lower bound. I need to find the parameters of my model, and I need to find the parameters of my encoder, which is my approximate posterior. I don't know theta, and I don't know phi. So, well, as usual, we have an optimization problem. Let's take a gradient with respect to theta, which finds the parameter of the model. Let's take a gradient of the phi, which is the parameter of my encoder. So last time when we were talking about variational expectation maximization, I told you that, well, taking gradient with respect to theta is not hard because this term is not function of theta. I can bring the theta in. But taking gradient with respect to phi is not that easy because I cannot bring that inside because this is also a function of phi. So we talked about these techniques that we can write it as a log, so we can multiply and divide by q phi, and then that looked like a log of some term. So you saw that. I'm going to show you another trick right now. One trick to do that is to say, well, Z. So remember how the Z look like. So the Z is we had this, right? So in some sense, the mean and the variance of distribution is a function of X. What if I have some canonical distribution that here I'm represented by epsilon that does not change with anything? It's just a fixed distribution. I'm going to use this function to map that distribution to any arbitrary distribution like C. And I'm going to use all of the budget of my parameterization phi as a mapping between this fixed form distribution, some canonical distribution, to Z. That's the general idea of the reparameterization trick. So I have some distribution that is fixed and some change of parameters. So give you an example. So let's say that if I want to have normal distribution of mu, so mu is fixed, and gamma, let's say that Z is distributed by this, I can use canonical distribution, let's say epsilon 0 and 1, and then how my Z would be. How can I make a Z as a function of, as a deterministic function of epsilon? Right? That's it. So if I have, let's say, another example is like, let's say I have multivariate. So if I have Z distributed by, what that my distribution would be? Any idea? The same trick that you guys did. It's okay to be wrong. Just give a suggestion. What should be the mean of Z? Mu. So it's mu. What should be variance of that sigma, right? So if I add sigma half, epsilon is going to do the job. Right? Or if I have sigma, which is Cholesky factorization, then that can do the job also. So what is this change of parameters good for? So remember that the first term that we had was change of, so let's say that I want to take a gradient of some function of Z and take an expectation with respect to the random distribution I'm drawing sample from it. Right? So I'm drawing Z from that. I want to compute expectation of some function, whatever that is. So one way to do that, if I can represent z as a function of this epsilon, right? So I can find a deterministic function that maps epsilon to z. Another way of writing that is z is deterministic function. All of the randomness is coming from epsilon. So I can effectively ignore z and write it as epsilon, expectation with respect to epsilon, right? Z is deterministic function, right? So far, this is coming from the fact that z is deterministic function. Now, because p epsilon is not function of phi, I can bring the gradient inside, right? Because there is no dependencies on phi. And now, all I can do is that I can say that, okay, how can I approximate these values? I can draw a sample from epsilon, plug that into my deterministic function of z, and compute this, an average. The simplest way of averaging is to draw one sample and plug that in. Right? This is one sample approximation. Make sense? And this is a reparameterization trick. So the idea of reparameterization trick is that you have some complicated distribution like z. Let's start with some canonical distribution that is parameter free. There's no parameter there. You fix all of the parameters. And you push all of the complexity to this change of the variable g. And then say that you are changing the parameters, you are responsible for matching the distribution. I'm going to be just fixed distribution p epsilon. The cool things about that is that my gradient can come inside, and my simplest Monte Carlo approximation would be using only one sample. So you draw sample from epsilon, plug that into g, plug that into your f, and that's an estimate. It may have very terrible variance, but it's just an estimation. Make sense? So if I want to draw it in the computational graph, the the original form was using q and phi, passing through the distribution and producing f. So I changed the variable and introduced canonical distribution. And the forward pass needs epsilon, needs x, needs phi to compute g, and that's your whatever you plug that into your function, whatever is a function of z. And your backward is basically take a gradient of f and with respect to z, and take a gradient of f with respect to phi, and that's your backward path. So for any deep learning, you need a forward path and you need a backward path. Your forward path goes through all of these, and your backward path goes through this. And you can use that as an intermediate layer in any graphical model, deep learning of choice. So let's go back to our learning. So given that z is just a deterministic function of my epsilon, I can basically ignore z and write this as a drawing distribution from my canonical distribution, and there's some transformation. The other question is that, well, what we did was we draw sample from epsilon, plug that into g, which gives us z, and plug it into our the terms inside of our expectation. That was my estimate of the mean. Is it possible that we can improve the estimation of the second term? So in general, when you're using Monte Carlo estimation, you have to be aware that Monte Carlo estimation usually does not have, so usually the variance is going to be unbiased, but it's going to have a variance, terrible variance, unless you're controlling the variance. The variance would not be good. So if there is any opportunity in your model that you can compute each of the terms or any of the terms in a closed form, you can seize that opportunity. So we do have opportunity to compute the second term in the closed form. So what is the idea? Let's revisit the change of variable. We started from some canonical distribution. We passed it through some function, which was our change of variable function, and it produces some arbitrary distribution for us, right? So Z can arbitrarily change the distribution from unimodal to multimodal distribution, right? So for example, G, if for example, G says that push all of the values that are here this side and push all of the values that are here this side, is going to produce bimodal distribution for us. So, but when you have change of variable, so if I have variable epsilon, if I pass it through some variable that produces change of variable, what is the probability distribution of Z in terms of epsilon? If I know G, forget about the parameters, let's say parameters are known. If I know the probability distribution of P epsilon, how can I derive the probability distribution of the PZ given from the P epsilon? What do I need? Distribution transformation. What is the general idea of distribution transformation? So for each Z, I have to find out what kind of Z's can produce that. And there's also compression into this transformation, right? So so for PZ, I can write it as P epsilon G inverse of all of the epsilon that produce this Z, plus some determinant of the Jacobian of Z given epsilon inverse. This is the general form of of change of variables, right? If I apply some function and do some change of variables, the change of variables shows up as a inverse of the determinant, right? So I can write PQZ given Z as P epsilon that we had plus minus log det of so-called, this is basically Jacobian. It's a determinant of the Jacobian. So the cool things about that is that the first term is independent of the parameters, and whatever parameters that you have in your change of transformation are going to show up in the determinant of Jacobian. So let's give an example. So let's say that I started with canonical distribution of n, I, and z. So my multivariate distribution is a mean 0 and variance I. And I pass it through some encoder, which can be any crazy function, to produce a mean and a variance. And then my z is going to be epsilon in element-wise product of variance plus epsilon, right? So remember, here I'm not showing it as qx. It is actually a function of x, but just to avoid the visual, the clutter in the notation, I'm just avoiding functionality as z, right? So my z is a deterministic function of epsilon. The same way that you guys did for multivariate distribution. So if I take a gradient, so remember that because of the change of variables, the probability distribution of the q phi z condition on x is going to be log of the p epsilon minus the log of the determinant of the Jacobian. So this is a constant term. It is not a function of phi. And if I take a gradient of the z with respect to epsilon, these terms goes away. And the only thing that shows up is this epsilon. And because of this element-wise product, it has very simple form. So that means that if you remember in my previous term, I should be able to write this term explicitly. There's no dependence on x. There's no dependence on z. So this term gets out. And I'm done. So I don't need to estimate this term. Yes?
If the transform function g is differentiable monotonic function, you can write it this way. But if that's not monotonic, probably
Doesn't have to be monotonic.
But you need to add several Jacobian determinants.
No. So the form of the Jacobian is that this is what I'm writing here is the general form. So this is called, so what I wrote here is like I meant so-called pre-image. So the G inverse does not have to be one number. It can be a set.
Yeah.
Then, but still that's correct. So you are right. So if it is not monotonous, It's not going to produce one Z. It's going to produce a set. But still it is correct. So all you need to say is that it's some function of epsilon, somehow, and some determinant of the Jacobian. So it all depends on the behavior of the determinant of the Jacobian, which incorporate all of this nonlinearity. If it is not one-to-one, then it's going to show up in determinant of the Jacobian. But a good point.
Can you give example, how can you change the unimode to multiple mode?
Oh, okay. So one example of that would be, let's say for simplicity, let's say that we are talking about univariates, just to make our life easier. So let's say that I define a distribution that does not, so and this is, let's say this is origin 0. So let's say I have a transformation that anything on the positive side gets a positive drift, and anything on the negative side gets a negative drift. And make sure that I make it smooth so that it doesn't make any abruptness. So for example, the transformation would be something like this. Yeah. So my transformation would be x plus that guy, that drift. So which means that anything is on my right is going to push toward right, anything toward left is going to push toward left. It's going to make bimodal distribution. And then this is also very powerful because you can transform any unimodal to arbitrary modes. So this is very powerful idea. But what I want to tell you is that with this idea, we don't need to, for the first term, we need Monte Carlo approximation, but for the second term, we can just plug that in, and this would be our approximation of the Z. So because this is not function of Z, it gets out of the expectation. It's not also function of epsilon, gets out of the expectation, and that would be your second term. And that's the beauty of that. So to give you an example, this is what it looks like if it shows ever. Okay. Either the site is down or okay, show that. So basically, this is the result. For example, if we applied on MNIST dataset. So if we applied on MNIST dataset, this is our code. This is our code space. So this is our code space. So here in this arbitrary example, so they assume that the dimensionality of the code space is 12 dimensions. It's going to be 12 continuous number. And if I play with each of these representation latent space is going to result in a smooth transformation of my reconstructed digits. That these are reconstructed digits. Right? So basically, so this is the way to map this, relating the high dimensional data to a lower dimensional representation, such that in a lower dimensional representation, things are the digits that are visually closer to each other, because it's a smooth transformation from one form of 2 to another form of 2, are closer by in the latent space. Make sense? And so yeah, so you can see that also in this video. So you can also become more creative in terms of forming the decoder. Nobody says that the form of the decoder has to be feed-forward neural network. Of course, you can use, depends on your application, you can use a proper choice for encoder and decoder. For example, if you're using images, it's natural to use convolutional form for encoder and deconvolution for the decoder. So it's because it has to incorporate the structure of the graph, the structure of your data, and convolution is much more appropriate than just like feed-forward neural network. Also, for example, if you are incorporating something like a language or a string, you can be more creative and come up with appropriate encoder decoder. So, for example, if you're using, you want to generate autoencoder to incorporate the structure of the graph in the string of the words, you can use LSTM to incorporate the dependencies between words, and that can produce the parameters of your network, parameters of your encoder and decoder. So what I'm saying is that this general idea of using encoding and decoding to produce the parameters of the latent space still applies, but you can be arbitrarily creative in making these encoder decoders. Okay, I'm going to finish with this slide on how we can use this for the general graphical model. If I couldn't, so today we won't be able to talk about GAN, and this is probably, what time is it? Might be a little bit of a stretch for this. So if I couldn't finish it, I'll continue from this point next class. So now you may say that, well, the graphical model that you use in variational autoencoder was too simple. So you had one queue that goes from the original space to a latent space, and from latent space reconstructed back. What about all of the dependencies that we have in graphical model? So you can extend this idea of variational autoencoder for arbitrary graphs. So here is an example. So if you guys remember the mixture model, so in a mixture model, we have observed data, tag of each of these observed data, and the theta that represent the proportion here. By theta I'm talking about, so this is the same thing. And gamma, which is the parameters of all of the mixture. So the gamma here represent all of these mixture distributions. All of this case, just to make it simpler. So this was the simple mixture model, if you remember. But what if you have data set which is more complicated? So for example, this is an example of the data set that the mixture model cannot explain it well, because each of these wings are not really Gaussian, so it's like a warp Gaussian. So if you use Gaussian as a likelihood, that won't be an appropriate choice. So how can I use variational autoencoder and extend this graphical model? So Matt Johnson and a few other colleagues basically extended this for a general graphical model by basically extend this graphical model introducing an auxiliary variables that you can think of it as a code space in variational autoencoder. And what I said is that you keep the graphical model that you want. So in a general, in a classical graphical model, this was your likelihood that you use, for example, normal distribution. You can use that normal likelihood here, but this is your code space. This is extra variable that I introduce. So this part of the model is the same as this part of the model. This is basically your graphical model, however you're assuming. We are going to relax the notion of likelihood by introducing this auxiliary random variable that acts like a z in VAE and pass it through this decoder. That's it. And this will result in relaxation of the likelihood. So you keep the structure of the graphical model, whatever that is. You introduce some auxiliary variable here is a code space, and that passes through a encoder to produce one. That's it. And that results in much better approximation and can be very flexible in terms of likelihood. So here I'm showing you an example, if that works. Does it work? Oh, okay. So this is basically the convergence, and you see that in the latent space. Oops. Okay. So, well, in the latent space is warping the space basically. See that okay. You see that in the latent space. So we start warping that to make it look like normal. Right? So you can think of this encoder decoder as a warping space. You remember what I told you about mapping from weird space to Z space, which was nice. So this is basically what this decoder does. And then you can also apply it for any arbitrary graphical model. So this was like the general. Doesn't stop. So yeah, so this was basically an example that this model can be incorporated in general graphical model. So in the interest of time, I'm not going to talk about GAN. So we'll continue our discussion next time, talking about generative adversarial network. Thank you.